While the Y-20B represents a major leap forward for China's strategic airlift and aerial refueling capabilities, it remains hampered by a number of technical, operational, and strategic disadvantages that limit its effectiveness compared to its Western counterparts. These limitations have become more apparent following recent public demonstrations and military exercises, including China's first confirmed aerial refueling operation involving a Y-20U and H-6N bombers in June 2025. One of the most immediate disadvantages lies in the Y-20U's refueling system. The aircraft uses a probe and drogue method for in-flight refueling, which, while functional, is significantly slower and less efficient than the flying boom systems employed by aircraft such as the U.S. KC-46A Pegasus or the Airbus A330M RTT. The probe and drogue system limits the fuel transfer rate, which becomes a critical bottleneck when refueling larger or multiple aircraft during high-tempo operations. This constraint reduces sortie generation rates and increases vulnerability in contested environments where time and exposure matter. Additionally, China has not yet demonstrated autonomous or multi-receiver refueling missions under combat-like conditions, meaning its system remains largely untested at the scale required for large force projection. Another key issue is the WS-20 turbofan engine, which powers the Y-20B and its tanker variant. While the engine is a milestone in China's push for military aviation self-reliance, replacing the older Russian D-30, KP-2 engines, it remains a relatively new system with limited data on long-term durability, fuel efficiency under heavy operational loads, or resistance to environmental stressors such as sand, salt, and high-altitude cold. Unlike proven engines like the CF-6 or RB211 families used in Western heavy airlifters, the WS-20 has yet to accumulate tens of thousands of flight hours across various theaters. This raises concerns over readiness, maintenance burden, and reliability in extended operations. Some reports also suggest that not all Y-20 airframes are yet fully converted to the WS-20, which may complicate logistics and fleet management. From a design standpoint, the Y-20's internal cargo compartment is slightly narrower and lower in height than the U.S. C-17 Globemaster III. This limits the types of oversized military vehicles or specialized equipment it can transport, reducing flexibility in certain strategic lift missions. While the aircraft has a payload capacity similar on paper, around 60 to 66 tons, it cannot match the C-17's ability to carry two medium armored vehicles or certain command and control shelters that exceed height or width tolerances. This design constraint reflects legacy design choices and may require China to either develop a larger airlifter in the future or accept load restrictions. Strategic mobility is another area where the Y-20 platform is disadvantaged. Despite the aircraft's intercontinental range, China lacks a global network of overseas bases, logistics hubs, or refueling partners. This absence of infrastructure forces the PLA Air Force to either overextend missions with mid-air refueling or rely on complex staging from friendly airfields, which may not be reliable or available in a crisis. Countries like the US and UK, by contrast, can rely on dozens of forward-deployed bases, prepositioned equipment caches, and aerial tanker fleets integrated with multinational exercises and operations. China's Y-20 fleet, while expanding, operates under a far narrower strategic footprint. Operationally, the Y-20 family has yet to prove itself in real-world combat or crisis response missions. Unlike the U.S. C-17, which has operated in Iraq, Afghanistan, Ukraine, and in dozens of humanitarian deployments, the Y-20B and Y-20U have never faced contested airspace, hostile fire, or the logistical chaos of high-intensity war. The only known high-tempo deployment was a non-combatant evacuation mission from Libya in 2011, using earlier transport aircraft. The Y-20's peacetime missions, such as delivering vaccines, disaster relief, and parts to allies, are meaningful but not tests of combat reliability. Another emerging concern, particularly in Western military assessments, is the lack of realistic, large-scale training among PLAF crews operating the Y-20B. While China conducts increasingly complex exercises, most appear highly scripted and involve smaller formations compared to NATO standards. Realistic mission training, including integrated joint logistics with naval and ground forces, contested refueling in degraded environments, and rapid tactical deployment drills, are still maturing. This raises questions about whether PLAF crews can fully utilize the Y-20B's theoretical capabilities under real combat pressure. Additionally, there is a strategic vulnerability in the Y-20 family's design philosophy. China is building multiple specialized platforms, transport, tanker, early warning off the same Y-20 airframe. While this improves manufacturing efficiency and fleet standardization, it also creates a single point of failure. Systemic design or engine problems could affect the entire strategic lift, refueling, and airborne command structure at once. In contrast, Western militaries typically spread those roles across multiple platforms. While the Y-20B represents a technical leap forward for China, especially with its indigenous engine and multi-role design, it remains hindered by slow and less efficient refueling methods, unproven engine reliability, cargo space limitations, lack of global logistical infrastructure, limited combat testing, and a developing training ecosystem. These disadvantages have become more visible as China starts to publicly showcase the Y-20B's operational roles, and they reflect the growing, but still incomplete, nature of China's strategic airpower capabilities as of mid-2025.